Kia ora. This is Ric Mann reading the first in a series of 16 cornerstone articles for lightcolourvision.org. At a steady canter, the reading time should be just over 40 minutes. If the doors of perception were cleansed, everything would appear to man as it is, infinite. For man has closed himself up till he sees all things through narrow chinks of his cavern. William Blake, poet, painter, printmaker, 1757-1827, The Marriage of Heaven and Hell. Light is everywhere. Look around. If you can see something, then it is being illuminated by one or more light sources. Sunlight, moonlight, firelight, street light, starlight, a firefly. Light is primordial. It dates from the beginning of time and is ubiquitous. It saturates the universe. Light is primitive, curling yellow and red in prehistoric hearths, flashing and booming in the dead of night, deadly in the midday sun. Light cuts through the darkness and through the shadows in our lives, drawing attention to things that would otherwise be hidden. Light wages war upon us, polluting, burning and blinding. But along with light comes illumination, insight, awe, wonder. When all else is stripped away, light is pure energy. Talking about seeing the light means to understand something more clearly or in new ways. As the veil of darkness lifts, personal realms are revealed. The mind's eye, imagination, hallucinations, and penetrating revelations. If we want to see more, we turn up the light, point the torch more directly, or concentrate our thoughts. Film studios and theatres are full of banks of light to make sure we see the action as intended. Shopping malls are full of spotlights to make sure we don't miss any details of the latest display. There is an illuminated stage in our minds where flashes of creativity spark new ways of seeing and acting. As searing light sweeps away the old, previously unimagined possibilities dance before us. If we can't see things through direct observation, then we insert equipment into our line of sight. Microscopes, telescopes, spectroscopes and oscilloscopes are all technologies of choice to enable invisible stuff to materialize before our eyes. Gamma waves, microwaves and radio waves, for example, are all types of light that are outside the visible part of the spectrum, but can be shifted to the range of wavelengths our eyes are best suited with the right piece of kit. Meanwhile, graphic visualizations can make data visible. MRI scanners create a kind of topography of the human body, and 3D printers can create artifacts from non-visual information. To get a grip on contemporary perspectives on light and their connection to colour, vision and ways of seeing, we're going to take a 13.8 billion year step backwards to the beginning of the universe. Our destination is a short time after the Big Bang. It involves a trip into the scientific worlds of cosmology and evolutionary biology to come to terms with core questions related to the fact that we have eyes. In case you're already confused, cosmology is a branch of astronomy that studies the origins of the universe, and particularly the way it has unfolded over time. Evolutionary biology studies the processes evident in nature, natural selection, common descent, speciation, that account for the diversity of life on Earth. The underlying rationale for the route we will follow is that there is nothing random about the fact that eyes have evolved on several separate occasions in different species, that we see the world around us with such clarity, or that sight is so central to how we learn about and understand ourselves and the world. There are direct connections between the earliest history of the universe, the formation of the first stars, the galaxies they exist within, and the fact that almost all insects and animals have little light-sensitive balls stuck on the front of their faces. We will pass important sites on the road that can be thought of as the preconditions for visual perception. So look out for the first appearance of light, the emergence of space-time and its geometry, the stability of the cosmos over time, material forms and embodied beings, biological life and photosynthesis, and finally, the emergence of eyes and human cognition. Let's begin with a photograph of a somewhat self-satisfied looking gentleman smoking a pipe and directing his nicotine-filled gaze into the machine that towers over him. He seems to want us to appreciate that he's making unparalleled discoveries about the night sky that will lead to brand new fields of scientific inquiry and a plethora of other remarkable discoveries. We now know that in less than a century, his work will transform our understanding of the cosmos and play a critical role in scientific revolutions set to transform our lives. What is not clear from this portrait is whether he knew that as we find ways of sense photons of light travelling from ever more distant reaches of space and time and decode them to reveal their origins and some of the details of their travels, a parallel process enables us to reconfigure the scope of human vision, the reach of our imagination, and cast new light on what it means to be a human observer. The Big Bang. So let's start by mapping out the context for the idea of there being preconditions for visual perception. In the photograph of Edwin Hubble, introduced above, we see a scientist peer into the eyepiece of one of a new generation of powerful optical telescopes. What he saw was a total revelation. During his research at the Mount Wilson and Palomar observatories, he made measurements and perceived details in the night sky not imagined by previous generations. Relying solely on evidence drawn from faint smudges of light, he was able to make unanticipated deductions about the scale and origins of the universe. The Big Bang is a scientific theory arising from measurements showing that the universe is much bigger than had previously been realised and is still expanding. Hubble was the first to make such observation and to publish his calculations in 1929. Hubble and his contemporaries worked out that there are myriad galaxies located beyond the boundaries of our own, the Milky Way. Their results also showed that regardless of which direction we look in, that clusters of galaxies are moving away from us, and the ones that are farthest away are moving the fastest. The remarkable thing that Hubble's observations demonstrated was that unlike releasing a box of birds in an open field, enabling them to fly off through space towards the boundaries of the field, it was space itself, and so the field, that was expanding. Taking this analogy a little further, when Hubble made his observation, every bird, cluster of galaxies, appeared to have travelled a considerable distance from their point of origin. But it wasn't so much that the birds were all flying away. It was that the scale of the field itself was expanding. As a result, we can imagine that even if each bird, or cluster of galaxies, were to be glued in position at some moment, the distance between them would continue to increase, not because they were going anywhere, but because the volume of the field itself was exploding in size. This way in which the universe was observed to be expanding came to be known as the Hubble constant. Of course, the universe is not a field of birds among other grassy paddocks, as suggested by the analogy above. Quite the contrary, the universe encompasses everything in existence, from the smallest subatomic particle to the sum total of all galaxies everywhere and everything else besides. The universe, past and future. What will happen over time if galaxy clusters, some of the biggest structures we know of, are drifting away from one another as the size and geometry of space and time changes in scale, leaving more and more empty spans in between? The answer seems to be that in the distant future they will eventually be so far away from one another and receding at such a speed that their light will fade to nothing as they pass out of reach forever. From then on, other than the relatively small galaxy cluster around our own Milky Way, there will be nothing out there but an impenetrable empty void. If that bleak picture lies in the future, what can we deduce about the past? What has brought us folk on planet Earth to this point in the history of the universe? Hubble realised that if the rate at which the universe is expanding is constant, then not only is it constantly getting bigger as time goes on, but looking back in history, in the past, it must have been smaller than it is now. Very slowly let the air out of a party balloon at a constant speed, and the speed at which it shrinks will also be constant. If we run the sequence of events that account for the evolution of the universe in reverse, at a certain point, 13.82 billion years ago, everything becomes so small it vanishes entirely. That vanishing point is the location of the Big Bang. Big Bang. It's a silly name, because at the moment the universe first appears, there is no space, no time, and no one to hear anything. But be that as it may, the Big Bang theory suggests that because the total mass of everything that constitutes the universe as we know it now was at one point in the past compressed into an infinitely small nothingness, that it was also off the scale hot. A parallel example of how things that are compressed become hot is the way a bicycle pump heats up at the point where you force air into a tyre. Pressure doesn't directly cause things to heat up, but compressing the same amount of gas into a smaller space does. The amount of heat in the gas remains constant, however, in a smaller volume, that heat is more concentrated, thus raising the temperature. In the case of the Big Bang, heat is usually attributed not to pressure, but to the wavelength of photons of light. As the Big Bang took place and space was in the first instant of materializing, there was only room for the very shortest wavelengths imaginable, at the top end of the electromagnetic spectrum where gamma rays are emitted. Gamma rays not only have the shortest of wavelengths, but they also transport the most energy. The more energy, the greater the heat. The gamma radiation we're talking about here had the shortest of all possible wavelengths and harboured the sum total of energy that would ever exist anywhere, ever. This was not going to just be a bit of a pop. It truly would be a tremendous boom. The Big Bang is the point from which everything in this article and the universe itself unfolds. In an unimaginably brief amount of time, the infinitesimally small space between any two imaginary points inflated to 99.7 trillion kilometres, causing a previously non-existent potential to actualise as a primordial plasma soup. As it decompressed, it began to cool, dropping to about 1 billion degrees Kelvin after the first few minutes. After this initial fraction of time, a slower expansion and cooling process continued, and in accordance with a pattern that seems to conform with the Hubble constant. For those interested in such things, the unit of measurement for the Hubble constant is estimated to be around 70 kilometers per second per megaparsec. A megaparsec, meanwhile, is a million parsecs, and as there are about 3.3 light years to a parsec, a megaparsec is quite a distance. It's impossible to visualize the matter radiation plasma soup immediately after the Big Bang, because even if we leave out its unimaginable explosive force, its defining features, including structure, density and temperature, were smoothly and indistinguishably distributed in all directions to infinity. As a result, the preconditions for the usual way human beings think of things, in terms of specific locations in space and time, and with a point of view on distinctive surroundings, didn't yet exist. Everything was identical everywhere. Cosmic microwave background. With that overall scenario in place, it's time to talk about light. Around 400,000 years after the Big Bang, things began to happen that are still evident today and are of relevance to the central concerns of this article. Using our latest technologies such as the European Space Agency's Planck satellite, we've been able to study the cosmic microwave background, CMB, a relic of the oldest known electromagnetic radiation in the universe. It began to be emitted as the chemistry of the opaque plasma soup mentioned in the previous section began to alter. This happening, in which photons of light began to be distinguishable within the preceding opaque plasma, occurred as the first forms of matter condensed sufficiently to produce discrete atoms of hydrogen and helium. It heralded an increasingly transparent future because the new atomic structures had empty spaces between them through which photons of light could squeeze. That process of the decoupling of matter and energy continued for another 600,000 years. Images of the CMB dating from that epoch provide evidence of the first visible signs of the universe we inhabit today. The cosmic microwave background is radiation left over from the Big Bang, and, as the word microwave reveals, it is electromagnetic radiation in the microwave part of the electromagnetic spectrum. Microwaves have a peak wavelength of 1.9 millimeters. This, however, is what we see of the CMB today. The gamma waves emitted at the start have been stretched by the continuing expansion of the universe over time. The cosmic microwave background was discovered by accident in 1965 by researchers building a new type of radio telescope. The telescope looked like a huge horn and was intended to be used as a satellite communications antennae. But things weren't going well because the scientists were puzzled by the constant hiss of noise it produced. They soon realised the noise came uniformly from all over the sky. Physicists who had first predicted the existence of the cosmic microwave background in 1948 then realised that this static was what they had been looking for. It would be another 50 years before another generation of space telescopes, such as Planck and its sister satellites, revealed that whilst being smooth and uniform in every other way, at a sufficiently high resolution, images of the CMB contain very small fluctuations in temperature. These fluctuations represent tiny irregularities that would, as the universe evolved further, precipitate the formation of ever more complex forms of matter and lead to the evolution of galaxies, their stars, and all the other structures we see around us today. It's important to be clear about how we can possibly observe evidence of CMB radiation if it was emitted so soon after the Big Bang. Microwaves are a type of electromagnetic radiation, EM radiation, which we often simply call light. The visible light we humans see is different from microwaves, ultraviolet light, X-rays, gamma rays and radio waves in that they are all invisible to the human eye. The only difference, though, between visible light and the other types is that they belong to different bands of wavelengths that we divide EM radiation into. All forms of EM radiation fall somewhere on the electromagnetic spectrum. Since all forms of light travel at a speed of just under 300,000 kilometers per second, the speed of light, through empty space, there is a delay between the moment light is emitted and its arrival at distant destinations. For example, the delay between light emitted by the sun arriving at our home planet is around 8 minutes. As distances get bigger, the time delay gets longer and eventually must be measured in light years, the distance light travels in a year. The delay between transmission and reception of light travelling across our local cluster of galaxies is 9.8 million light years. On a bigger scale, there are 3 million galaxies within 1 billion light years of our solar system. This means that as light arrives, we see things as they were all that time ago. The light from the CMB has travelled further than any other before being picked up by equipment like the Planck satellite, telescopes designed to pick out the CMB from all other types of EM radiation in the sky. When astronomers observe the CMB, they see it as it was more than 13 billion light years ago. The CMB appears to be the same distance away in every direction. The implications of this are that we can think of ourselves as having a viewpoint on the universe from which the CMB forms a sphere around us. But it's not that it's all laid out just for us. The fact is, as far as we know, whatever the viewpoint within the known galaxy, it's so huge that the CMB would always appear to form an identical sphere. This is hard to visualize, as is the fact that it has now cooled from its original superheated state to just a couple of degrees above absolute zero. The extraordinary thing about all this is that planet Earth, an unremarkable ball of matter in an equally unremarkable corner of the Milky Way, has developed blobs of biological matter that are able not only to feely-crawly themselves about the ground, but can sense forces that have shaped everything that has ever existed anywhere since the beginning of time. Life on planet Earth is truly insignificant, yet human eyes and human minds are tuned to the cosmos and to processes that shape the largest objects imaginable and at the same time account for the subatomic particles that provide their foundations. Theatre, stage, actors and eyes. It's time to break down the ground covered so far to extrapolate the interconnections between the cosmological, biological and sentient dimensions of our lives. The building blocks introduced already mark out large-scale connections between our contemporary everyday experience and the most distant reaches of space and time. To conceive of this sense of connection from the largest to the smallest scales has required massive feats of imagination and has drawn on the genius of some of the world's greatest minds, including familiar names such as Charles Darwin, Albert Einstein, and Stephen Hawking, among many others. But today, appreciation of the structural interconnections between the Big Bang and the world as we see around us is in evidence wherever concepts such as universe, cosmos, evolution and emergence are found. Whilst each one of these has already been used in previous sections, let's summarise each in turn as we get down to the business at hand. The universe includes the whole of space and all forms of energy and matter. In more descriptive terms, we can talk about the totality of existence, which is to say everything that exists now plus everything that has ever existed or will exist. The inclusion of thoughts, emotions, feelings and physical sensations adds a human sense of scale. The term cosmos treats the universe as complex but orderly interrelated systems. It implies the accumulation and variation of generative and developmental changes over time in the composition and assembly of radiation, matter and life, including humankind. What neo-Darwinism does for the biological evolution of plants and animals and their intimate interconnections, cosmic evolution does for larger categories and entities. Cosmic evolution provides a continuous framework within which to consider the systemic properties and sequential relationships between the describable properties of the universe. Cosmic evolution might be broken down into subdivisions such as the following: evolution of primal energy into elementary particles and atoms, evolution of those atoms into galaxies and stars, evolution of stars into heavier elements, evolution of those elements into the molecular building blocks of life, evolution of those molecules into life itself, evolution of advanced forms of sentience, evolution of intelligent life into cultured and technological civilizations. To provide a sketch suited to present purposes, it's sufficient to simplify the overall span of these divisions into just 3 eras. The era of matter begins with the emergence of space-time as discussed above. It encompasses the period during which elementary forms of matter became evident and includes their progressive differentiation and chemistry. This era is inclusive of the appearance of the first stars and of all the properties of the universe we see and study in astronomy and the other physical sciences. By comparison, the era of life is a more recent phenomenon. Life as we know it is very localized but forms an overlay of properties both dependent on and distinct from matter. Life has emerged, flourished and evolved the ability to entirely reshape and add novel properties to its material origins. What might be called the era of sentience includes, but is not limited to, our very anthropocentric sense of things. It emerged only recently compared to the overall duration of the eras it overlays. The speed and degree to which sentience has gained sway over both the material world and life accounts for the introduction of a new geological term, the Anthropocene. It is from this location and with the aid of its emergent properties that we trace our cosmic heritage, its origins, chains and sequence of events, and a virtual blueprint that maps our survival over time. In what may seem to be an unreasonably ambitious task, let's try to treat the notion of life to the same scrutiny. Life is, in addition to the ways matter differentiates itself, it is energetic, material and chemical, but has properties that cannot be accounted for in those terms alone. Life, in this sense, is a process internal to matter, not a force or a property applied from outside in the way strings are used to manipulate a puppet. Life is then not a vital force, but rather a supplementary property inherent to matter. Life differentiates itself from nature from within, a dynamic self-containment functioning across a porous boundary. It feeds upon and feeds back into its surrounding. It folds materials and their chemistry into itself, whilst unforeseen properties emerge that it uses to continue the process, folding within folds. Life in this sense can be understood as parasitic on matter, as it draws from its chemistry the forces and information it needs to reproduce the impetus to persist, so to exist. Living things are all variations of life, each one uniquely different from another, and in every case able to adapt to or readapt its material conditions, regenerating itself from within before its willfulness is exhausted. The common impetus all its forms carry is that of materiality itself, the capacity to extend the extant, to reach out and recreate itself in new and unforeseen terms. Sentience supplements life and inorganic matter, just as matter supplements space-time. But running in the other direction, space-time is meaningless without matter to fill it. So equally, space-time, the organic, the inorganic and life are all meaningless without sentience. So with sentience comes yet another supplement, meaning itself. Now let's put this framework into effect. It helps if we think of human life as a play. Here we are, living out our lives and getting on with things as best we can. Then there's the stage on which we find ourselves, the natural world and our ecological niches within it. Housing all that is the theatre. Electromagnetic radiation preceded the formation of the first stars. What we call the cosmic microwave background was the first manifestation of light and the first evidence we have of its earliest workings. For this reason, light is enmeshed into those laws of physics that help us account for the consistent forms and properties of the heavens across all space and time. The fact that photons of light began to escape the preceding torrid isotropic mass of superdense plasma and traverse the empty spaces between emerging atomic structures accounts for the fabric of space-time. Both space and time are the fundamental prerequisites for a material universe. All forms of matter, including every living thing, must have geometric coordinates and be capable of negotiating trajectories between things if they're to exist. And this is exactly what space-time provides. Space-time is the dynamic theatre that determines the physical and temporal dimensions of the stage on which we find ourselves, and thus the locations from which we participate in the play into which our lives are woven. Each of us is, in that sense, an actor, swept forwards by the tides of time, caught in the action as things emerge, evolve, change, and become different. It will be billions of years after space-time emerged that sentient creatures evolved on planet Earth, able to reflect upon their place in this matrix and trace its history back over eons. But eventually, generations, including our own, can see and consciously appreciate that our very existence is predicated upon conditions that began to emerge in the earliest phases of the evolution of the universe. How remarkable that we can describe ourselves in those terms. Another crucial detail, if we're to properly account for ourselves as sentient, concerns our bodies and their existence among other things. In other words, what are the preconditions for the embodied existence of anything? As we extrapolate the interconnections between light and vision, we need to keep in mind this very material fabric of our existence. To grasp this, we must target the physical matter that everything from our diminutive skeletons to the celestial bodies above our heads is constructed from. All of the material mass of matter in the universe emerged along with the massless energy of the cosmic microwave background. CMB radiation was emitted as atoms of hydrogen and helium formed. Initially, these were the only forms of matter, and even today, hydrogen is the most abundant element in the universe. Because of their mass, hydrogen atoms began to clump together under the effect of their own gravitational attraction, forming sheets and walls and filaments separated by immense voids, creating the vast structures sometimes called the cosmic web. As ever larger quantities of hydrogen were drawn together, gravitational attraction increased, accelerating great clouds into ever smaller and hotter regions until the first stars and galaxies were born. Stars are balls of burning matter undergoing nuclear fusion within their cores and forcing atomic nuclei to fuse and produce new, heavier elements. During the fusion of two hydrogen nuclei to form helium, for example, a little less than 1% of their mass is emitted as energy. This process, which continues today, is the source of all the light that overlays the CMB. Within our solar system and our local star, the Sun, it is this same process of fusing hydrogen nuclei that releases the radiant energy that bathes our world in light every day. Whilst the first stars were composed solely of hydrogen and helium, the rest of the elements found in nature are the result of nuclear fusion within later generations of stars and from catastrophic stellar explosions known as supernovae. The most common elements like carbon and nitrogen are created in the cores of all stars as they age. The aging of larger stars produces heavy elements such as iron, but it is supernovae that produce the remainder of naturally occurring elements seen in the periodic table. During the greater part of their lives, gravity pulls the contents of stars together, whilst fusion pushes them apart. The two balance each other perfectly until fusion stops. When stars over a certain size run out of fuel, it causes the outer layers to explode and the core to implode, producing a core collapse supernova. It takes about a quarter of a second for the entire core of a sun to collapse in on itself in this way. The massive increase in pressure in the extreme conditions of this type of supernovae adds new and even heavier elements to the list, cobalt through to plutonium. Without preceding generations of stars and supernovae, planet Earth would be a very different place and life as we know it would not be possible. Without all the naturally occurring elements of the periodic table, there would be no rocky spheres like our own, only gas giants like Jupiter and Saturn, no seas, no mountains, no solid cores and no bodies. We need all the elements within our atmosphere to breathe. We need carbon to build bones. Our blood has iron in its hemoglobin, which carries oxygen to every single cell. Nitrogen enriches the soil and is a vital component of chlorophyll. Chlorophyll in turn is the compound by which plants use energy provided by sunlight to produce sugars from water and carbon dioxide, photosynthesis. Nitrogen is also a major component of amino acids, the building blocks of proteins, and without them, plants and bodies wither and die. To fully appreciate the materiality of our bodies, we must remember that the idea we're stardust is not just a poetic metaphor. The entirety of our solar system is composed of material from the cosmic web and past generations of stars. Every atom in our human frames has an extraterrestrial origin. And when people muse about whether there are aliens out there in space, they forget that our bodies are where the real aliens are hiding. It's just that the aliens are the building blocks of every molecule and compound from which each of our organs and sinews are constructed. But whilst the matter that forms the bodies we live in is extraterrestrial in origin, there is, as yet, no compelling evidence that life itself originated elsewhere. Bodies, beings, organisms, entities and multicellular life forms. These are some of the names we give to the living creatures we share our biophysiology with. Every plant and animal is distinguished by an individual material existence bounded by birth at one end and death at the other. This is life as we know it, and every instance represents another extension and elaboration of matter and energy. All the different things living organisms do with light accounts for the sheer abundant volume of our shared biosphere, its spread, diversity and evolution. We must look once again to light to account for the animation of matter, the emergence of life, and for our entire biosphere. It is photosynthesis that has been at the heart of that interface for the past 4.6 billion years. Life has been shaped and driven by photosynthesis, and it forms a key part of the root of life's family tree. Photosynthesis harnesses the electromagnetic energy carried by photons of sunlight and turns it into chemical energy. There are two types, oxygenic and anoxygenic photosynthesis. The general principles of both are similar, but oxygenic photosynthesis is the most common and powers all plants, algae and cyanobacteria. Chlorophyll within leaves and stems of plants absorbs the light and synthesizes carbohydrates such as sugars using carbon dioxide and water drawn from the environment. Different wavelengths within the visible spectrum corresponding with particular colours play an important role in photosynthesis, but plants don't absorb all colours evenly. Chlorophyll absorbs violet, blue and red, but all green wavelengths are reflected, hence the apparent greenness of nature. If evolution hadn't come up with photosynthesis, there would be no oxygen in the atmosphere, no protective ozone layer above it, and probably no life on dry land. Planet Earth, minus the intervention of photosynthesis, would be anathema to the higher life forms around today, and would be populated only by primitive bacteria in oceans or deep in the soil. Since the advent of photosynthesis, organic life and the planet have co-evolved. Forests turn to coal, seashells turn to limestone. Plants draw the nutrients and water they need from the soil. Even plate tectonics may play a crucial role in nourishing life. Organisms and biosystems draw upon what remains of the light absorbed by the generation of life forms that have preceded them. The continuity and unity of life that we know today is evident in the uniformity of genetic systems, the molecular composition of living cells, and the chemistry that folds in and out of living things. But it seems that photosynthesis has its limits. Is there a boundary in terms of complexity and the concentration and transmission of information that plant life cannot achieve? Animals don't produce chlorophyll, nor do they rely on photosynthesis for energy. All observable forms of sentience and self-awareness fruit on the higher branches of our evolutionary tree, and it is up there that we find animals with eye holes. New connections between light and life emerged along with the animal kingdom. Even though the kingdom is diverse, animals share common features that distinguish them from other organisms. Animals are incapable of photosynthesis but rely wholly upon it as they ingest living and dead organic matter and each other. Almost all animals have specialised tissue that form organs, not least of which is the central nervous system. Offspring pass through developmental stages that establish a determined body plan, unlike plants, for example, in which the exact shape of the body is indeterminate. At one end of every animal body is the head, where the nervous system is most densely concentrated and from which cords of neurons extend towards the surface, breaking out into a profusion of light-sensitive tips. It is as if the central nervous system reaches outwards to sense the world beyond itself, but not just to see its surrounding, but also to search for some evidence by which to account for its own existence. In The Origin of the Species, Charles Darwin noted, "How a nerve comes to be sensitive to light hardly concerns us more than how life itself first originated. But as some of the lowest organisms are known to be sensitive to light, it does not seem impossible that certain elements should become aggregated and developed into nerves endowed with this special sensibility." Some of the early forms of eyes looked like small spots before evolving into concave cups and then developing lenses, and so a more successful and competitive organ for sight. The process probably required around 364,000 generations, so a shorter period as 500,000 years. Our eyes are exactly tuned to respond to the band of energy between red and violet that can make its way through the atmosphere. It is this same range of wavelengths that powers the entire canopy of life that covers the planet on land and at sea. When light strikes a photosensitive rod or cone cell in the retina of the eye, it releases energy and triggers a chemical reaction which in turn produces an electrical impulse that, after processing, is transmitted to the brain. It seems likely that from the moment the chemical reaction begins, that the energy received contributes in one way or another to visual perception, and in humans, so to conscious experience. Initially, eyes probably could distinguish between light and dark, but it is theorized that the prototypical ability to distinguish between organism and environment may also have been an early function. If you've seen the film 2001: A Space Odyssey, you will have your own conception of the point at which animal species began the long haul from the distant reaches of sentience towards tools, artifacts and images. The rite of passage to the last in our series of interconnections between the cosmological, biological and sentient dimension of our lives. Imagination. Imagination. The opening paragraph of this article centered attention on the connections between light and sight and the question of why so many creatures have developed eyes. Subsequent paragraphs provided a brief tour of the early universe and the place of light within it. In the preceding paragraph, a concerted effort was made to trace out more details to substantiate the links between the dawn of the cosmos, the advent of matter and bodies large and small, the dependence of life on photosynthesis, and the appearance of eyes. The links between each facet of the account are emergent in the sense that new properties emerge once necessary preconditions have been met. Emergent properties arise from interactions among the parts of a whole. In this sense, life, as studied in biology, is clearly an emergent property of chemistry, and eyes couldn't evolve before bodies. Taken as a whole, we can make the speculative claim that eyes are themselves an emergent property of light. The point is, without eyes, there would be no experience of light. And had eyes not evolved, we would not only be unable to see, but there would be no visual component to our world. Can you imagine a world in which the sense of sight had never existed? Until life developed on Earth, the cosmos had never seen itself. Only living things can sense the existence of the world. Without us living beings, nothing from a speck of dust to the whole of the night sky knows anything about our reality. Without us, matter and energy exist, but they don't know themselves because they cannot create an image of their world. Eyes connect our experience directly and instantly to electromagnetic radiation, to the visible spectrum, to colour, and to everything between here and eternity that can be described in terms of one aspect of visual perception or another. Without our eyes, the cosmological scale of the universe would be beyond the reach of our other senses. It would be impossible to picture what is out there beyond earshot and the sense of smell. Its scale, how it changes, its history or future. Without images of these objective dimensions of our world, our images of ourselves and of our own lives would be similarly blinkered. Without the benefits of visual perception, we will be little more than those squishy slime balls stuck by gravity to the surface of an insignificant sphere of rock, blindly living out our lives within its narrow envelope of atmosphere with nothing beyond. It's easy to take our sensory experiences for granted, but because so much of our day-to-day lives centre on images, vision is, without any doubt, the faculty we need to be most critically aware of. Unless we explore and critique the economic, social, political and cultural forces that shape our perspectives, our horizons remain narrow and parochial. Left alone, most of our experiences, whilst figuring so prominently in our worldviews, largely exclude an ability to cognise the implications of our own everyday behaviour, the road our species is taking or the direction in which it is heading. Animal exploitation, environmental degradation, domestic violence, homelessness, illness, poverty, prejudice, racism, slavery, social inequalities, starvation, war, among others, affect millions of human beings and our natural world every day. To recognise, understand and know how to address such issues requires a type of vision and forms of imagination that can only be developed over time. The powers of discrimination that enable us to decode the ways we see and understand the world must be nurtured to prevent the wool from being drawn over our eyes. We must constantly re-envision ourselves, our lives and our potential. As far as we know, life on Earth is the only life anywhere. At best, we barely exist in relation to the scale of everything around us. The lifetime of even the most enduring species are brief sparks in the history of our solar system. In terms of the size of the Milky Way, there just are no dots small enough to represent ourselves. The existence of life itself registers only in our own minds and those of a small family of animals around us. The news has yet to reach the galaxy next door that Homo sapiens evolution is imminent. The Andromeda Galaxy is 2.5 million light years away. Beyond that, galaxies like our own, huge as they are just fading sparks. The point is that in the end, it all comes down to how we want to imagine ourselves. We can look around and see how small we are in relation to everything else. We can fill our minds with trivia and live the life of couch potatoes. The more we constrain ourselves, the more tightly we draw the frame around our imagination, reducing its scope and content and veering towards the point at which we feel completely hopeless and alone. Or we can do the reverse. The larger the frame, the more light and the more life gets in. We choose. Select a frame to be human. Select another to admit animals, and then planet Earth. Expand further to grow tendrils across interstellar regions of time and space and reach towards other worlds. Become timeless. The possibility of looking beyond ourselves is always wound into the present tense of our existence. Reach far enough and we can see the whole of the universe in a grain of sand. Well, how did we do? If you think this article needs further development, please join our panel of editors undertaking the first phase of editing and send us your feedback to help us to make improvements.